This is tricky. We're going to talk about old file system after talking about Zinco and GUIs and all this stuff. So you may have this completely known by heart, but I go over once again some of the basic concepts of the way the file system works. We've talked a lot about store nodes. This is the lowest level on the system. Scale out object storage. It's a shared nothing distributed system that stores the slices of data. On top of that, we run connectors and these erasure coding schemes. As was mentioned, we either use replication or erasure coding to protect the data spread across the nodes. And then at the highest level, we have file system interfaces and object interfaces. So this is basically the way that the system works. One of the key elements of it is that there's no master on the system, and that's one of the reasons that we have no hard limit on how large the system can grow.
Can I build a correlation between an S3 bucket and a NFS mount point so that I can create data from my existing applications and then have it sucked in by something that speaks S3?
So there's a lot of complexity to that question. There's kind of two different worlds. There's a pure object world and there's a pure file system world. I'm talking about the pure file system world right now. Now we do have a way of consuming file system data as S3, and I'll talk about that.
Yeah.
The S3 that we've been talking about, Zinco, is a very much an object world,
yeah.
Meaning that you write an object and then you overwrite the object. And here we're talking about the file system world, where you modify little blocks of a file. So that's true, but there's basically two ways that we can do this, and I'll specifically concentrate on the file system way. We're going to be introducing file system interfaces to the object model, which will give you a way basically to export a bucket as an NFS mount point. If that answers the question. So, but it is a little bit complex because the two worlds have overlap and non-overlap.
Well, I mean, a lot of systems will present a file interface and an object interface, but not to the same data.
Right. So we can do that with both worlds with the limitations that.
Yeah, but there are 47 billion applications in the world that speak POSIX.
Right.
And there are several 100,000, 20-something programmers who won't write to POSIX. They only want to write to S3.
Right.
And so there are times when I want a file and an object to map one-to-one and be accessible both ways.
Absolutely. We understand the need and the challenges associated with it. So we're working on it.
But the answer is not today.
Well, the answer is today. No, the answer is absolutely today. We can do S3 with file system, and I'll show you that interface at the end. But there are complexities to the model. It's an imperfect.
There are complexities just to doing NFS and SMB on the same data.
Absolutely.
Absolutely.
Absolutely. But they're even worse.
I expect complexities.
They're even worse with S3. So, shared nothing architecture. This was fundamentally designed as the beginning as just a simple object store, and we decided how can we build a file system on top of this without losing the interesting properties of an object store. So what we did was we developed a fully distributed metadata engine based on an object model. This is a B+ tree. The file data becomes basically immutable, and only Mesa database main pages are modified. So you have a B+ tree that manages directories, and then we use basically a sparse file model to do file creation so that we can modify large files without having to overwrite a large file. And that's the giant difference really between a POSIX file system and an object model. If you write a gigabyte file in an object model and you modify your gigabyte file, you pull the gigabyte out, modify a byte, and push a gigabyte back. In a file system model, you don't want to do that. You want to be able to modify a tiny block of data and push that back. And this Mesa basically allows every file to have its own little database of where all the stripes are at, and then the file system tree is a giant collection of little tiny databases, one per directory, and that allows the system to scale in a sense without bound in the number of directories and the number of files and the sizes of the files on the system. So you saw Yannick showing two rings, a data ring and what he called a metadata ring. So the objects that we use in the metadata ring are generally stored on SSDs to improve the metadata performance. And so it's the same design of the system, but it's a separate ring with all the data
So a
stored.
single file can exist over multiple objects, you're saying?
So typically a single file will have quite a significant number of objects, and the typical stripe size, to use the sparse file term, would be on the order of a megabyte. And then that would be erasure coded. So a gigabyte file will literally be thousands and thousands of objects in the ring. So some of the things that are unique about this design, we can really do unlimited file sizes. There's no hard upper limit to how large a file can be. If you're really dealing with large files, you can do 32 megabyte stripes, for instance, on the files. We're also very efficient with small files. We containerize what's stored on the system so that there's no wasted space for very small files. And we very naturally switch back to replication when erasure coding doesn't make sense. Typically about 64 kilobytes. It's not worth the overhead of erasure coding.
But we're certainly not going to tell anybody this is going to be a primary storage use case where you're going to be editing files in any kind of frequency, right? Because I mean, obviously, like you said, if I have one thing that's 1,000 objects and I do a little editing and bit shifts and move stuff around, I got to go rewrite a whole thousands of objects again.
No, so you only have to rewrite the stripe. So if you have a gigabyte file, we actually have some people doing a certain amount of media editing.
Well, if I bit shift over,
so you can do very small modifies to a very large file. No problem at all. So it's a true POSIX system that you do very typical POSIX instructions on it. I wouldn't use it for database, but people are doing it for video editing, video transcoding, things of that nature. It's very fast for writing very, very large files. It's not very fast for doing byte-wise modifications like in a database. We use 64-bit inodes, so you've got basically a sufficiently large space on any single file systems. And then we can support up to 4 billion volumes on a single ring. We've never tested 4 billion volumes, but those are kind of the numbers. Those are the only really
Because Jerome wouldn't let you build one big enough.
only limits really number-wise on how big a file system could be. We have very flexible erasure coding schemes. I mentioned the idea. A typical erasure coding scheme that we use today is 9 data chunks plus 3 erasure code chunks. That makes a 1.3 overhead. And one thing specific about the way we do erasure coding is that we keep the data intact, original data. So there's a zero cost read of the data on a healthy object. And we have a number of ways of distributing systems across multi-sites with erasure coding. I'll talk a little bit about that. So there's really unlimited horizontal scaling in the sense that there's no hard limit on how many servers that you can run on a platform. We have platforms with over 200 servers running today. We have...
So, quick question, what are the performance constraints on a customer who wants to get data out of that cluster at a particular rate? Are there any magic numbers that you design by?
So the typical workload will be inputs to the sizing. Obviously, the throughput of the system depends on how many servers, how many spindles there are. It's really directly linearly related to how many spindles there are. And when you're pulling out a very large file, you're literally asking all the disks on the system to contribute. So we're typically saturating Ethernet interfaces on a single connector. For instance, if you're pulling out a single large file, we'll typically be saturating SMB and FS connectors, pretty much saturating a 10 gigabit link on a single connector.
In practice, it sounds like you're bound by network capacity. Is that what you're saying?
We're bound by network and by disks. I mean, hard drives have this.
So you're only as strong as your weakest. A chain is only as strong as its weakest link. So generally speaking, what are you seeing in the real world with your customers?
I would say we're very good at very high throughput applications. This is used a lot in media applications. I don't have numbers for any specific customers, but we have a number of customers running several gigabytes of I/O through a system on a pretty constant basis through the system. We have a number of different geo models that I talk a little bit about. We have a very interesting model that's a synchronous 3-site active system that allows your system to be stretched across 3 sites. You can lose any one site with basically no significant impact. No impact on the availability of the system and no significant impact on the performance.
Did you say synchronous?
Yes. So we're talking metro area, kind of a stretch of the system. We have a number of these systems deployed in metro areas. So yeah.
I just have to reset to, I don't have to wait for the tail end latency of the 3 sites across.
So typically you'll have like a metro area or we're talking sub 5 milliseconds and very often sub millisecond latencies across the system. But it is very interesting. We actually had a customer in the Paris area that moved one of their 3 sites while the platform was running. Moved this, packed up the servers, moved into a second site, plugged them back in again.
Do you have any customers who have data protection requirements outside of the cluster itself? Because it could be considered a single fault domain?
We have customers that think about it a lot. We have very few that have actually done anything about it.
Because of the scale.
Because of the scale.
Backing up 30 petabytes is going to take a while.
Exactly, and very often they're already in a situation. Some of these are using it for backup, and this is,
So how do you mitigate that?
Okay.
So a customer says, okay, we've got a single cluster, something goes wrong, the entire cluster is wiped out from a metadata perspective.
Go.
How do you recover?
Exactly.
Yeah, we do
but
have.
that's
We
not a
do
GA
have,
product.
now one of the options we have is an async replication to ourselves. So if there was a software bug, unfortunately none of those things have ever happened. But
Yeah, that's one of the kind of classic object storage conundrums.
Yep.
Is object storage robust enough that I don't have to back it up?
right.
And most of us have come down on probably yes.
That's, I think in a lot of ways, and a number of our customers are in a situation they don't have a lot of choice, and so they definitely put a lot of trust in us. There's no doubt about that. Some systems
so what
are
about-
backing up to tape.
What about protection from operator error? Fat fingering,
Yeah.
incompetence, malicious intent?
So I'll talk a little bit about some of those things. It's always possible, obviously, to destroy a system if somebody really wants to. There's, if you fill your data center up with water, that you'll lose your data.
I prefer thermite, but yes.
But yeah, I mean, there's so those are discussions we definitely have with people. Some people who absolutely feel that they've got to do something will do something. We do have a system, a stretched 3-site system. A couple of those systems, they decided to do that because they'd had availability problems. So definitely very powerful from availability. As far as durability, there's a lot of questions that people need to ask and make decisions on.
Yeah, you have a slide on volume protection? Maybe?
Yeah, I have a slide on the volume protection that I'll talk about that one specifically. So we also have a 2-site active with a witness 3rd site just for metadata, basically the same performance as the 3-site. And then we have an active passive with replication with very good management of the recovery point.
Do you have worm policies?
We do, and I'll talk about that. That's in a future slide. Some of the things that we've been working on and have completed is improvements on having volume-based quotas. We have user and group-based quotas. Now we have volume-based quotas. We have an undelete functionality that can help with some of the fat fingering on the system. And we have a volume protection that I have a specific slide about that's an interesting feature that some of our customers have specifically asked us to implement. Basically what happens, you write files to your system. There's a timeout, say 30 minutes or an hour. Once the file has been written, it becomes read-only, and you can't delete the file. We actually had some people in the intelligence industry that were writing files. You can think of a hard disk being replicated to the system. Someone was scanning the hard disk for forensic evidence, but their antivirus found a virus in the disk, and so they modified the evidence, and that was that was not what they wanted to happen. So that's an interesting usage for systems like that when, for instance, forensic evidence, the data is stored in the system. Things like body cams and things like that, it's an interesting model. So anything that's used for evidence, the file system becomes read-only. The only one who can modify the file would be a root user that would have to very carefully go in and introduce a new connector that doesn't behave like the others. And this has been a pretty interesting function for some of our customers. Also very interesting if you have some sort of a virus attack on the system. And we're investigating the possibility of being able to turn this on in the event of a detection of a
Have you
an
guys done
attack.
any third-party verification of that for 17.4 purposes?
So as of now, it is not an attempt to get all the way to there. It's just a functionality that protects your data, but it's something to think about. And then another a step up delete, undelete. I'm sorry, volume protection is file versioning that allows us to have multiple versions of the files in the system. The file versioning allows you to recover basically old versions from a recycling bin. And then we're going to be introducing next year a functionality, a point-in-time view of the system. It can be defined on a volume basis, and you can change the ACLs of the version so that the user can either self-restore or require the
So
administrator
it
to
ties
restore.
into the previous versions UI in Windows?
No, it's a hidden folder.
Okay.
So it's the
Someone could
old
probably
dot-
make an extension, though.
What's that?
Someone could probably make an extension.
Yeah, that's it.
Yeah.
And that there's a published API for that.
Yeah.
It potentially could. I talked through this.
What kind of policy controls do I have over previous versions?
So you'll have a policy that prunes previous versions, and we're implementing more sophisticated policies as we
When
speak
you say
now.
previous versions, that's not snapshot cycles. It's
Right.
when there's a write to
when,
the drive.
when there's a right
So objects
to the
work
drive.
anyway. It's
Yeah.
MS3 objects work, right?
Exactly.
Well,
Right,
it's actually a close, right?
Right,
Yeah.
right.
Okay.
Okay.
You need a don't allow more than X
Right,
versions.
right. Policy, yeah.
Well, it's not, there's store X versions, but you also need don't allow more than versions to be created faster than X.
Right,
Ransomware protection.
right.
Because they're getting smarter and they'll overwrite the same file 50 times. And if I keep 8 versions, but if I don't keep more than 1 version a day, I can still revert.
I
Right.
think, yeah, that's true.
Interesting. We're seeing a lot of those kinds of behaviors becoming a concern. And that's one of the reasons we think this is a very interesting, this write once, read many for the files. If you have data, and we have quite a few customers using the file system for that, writing data that they want to keep for long periods of time. An archival sort of a notion, and then all of those problems go away. So I think that's a pretty interesting usage for the system. I talked a little bit about this already. This is the 3-site stretch model, 3 data centers, erasure coding across the sites. We'll typically have about a 1.8 overhead across 3 sites. When we stretch across 2 sites, it's actually more expensive because you have to have more than 1 copy on each of the 2 sites. And there we flip the erasure code scheme, 5 data chunks, 7 erasure codes, so that if you lose an entire site, you have all of your data plus 1.
Okay.
And so that's the typical
So
models.
Most systems that do erasure coding like that, when you do a read, it recalls all the strips and then builds from whichever ones come first.
So our policy for the erasure coding in the stretch model, and that's one of the reasons we require relatively low latency, is we just pull back the primary data and we're just concatenating data.
You'll pull back the data strips and you only
Data
access
strips,
the
right.
parity strips if you need them.
Exactly.
That's better than the way most people do it.
I mean, we built the system around the notion. That people wanted their data in human scale times.
Yeah, you have to kind of balance the network bandwidth requirement
right.
and the latency when anything goes wrong.
Right.
And
And a stretch system like this, where you typically, except on the 2 sites, you could possibly do something a little bit more clever, but overall, it just hasn't been worth it to dig into not mess with that.
yeah.
So this is the 2-site asynchronous model. a ring on one site, a ring on a second site. Obviously, you can cross-replicate and have both sites primary for half of the data and secondary for half the data. But this model allows you to do a full sync in between the two sites. One really nice feature of this is that the inodes are mapped, are identical between the two sites, which means that hard links survive the replication to the second site. We can provide throttling in case the load on the active site is being affected by the replication. We can provide alarming if you exceed a delay time that's been configured on the system, and you always have constant monitoring on how far behind you are on your second site. So it does very, very parallel access of replication.
Do you have any customers who have a third cold site and will have a 24-hour delay on the replication, specifically for if you have your two synchronous clusters, let's say, get wiped out, and then you've got that cold site to rely upon that's always 24 hours behind?
No air gap.
It's been discussed. No one's ever done it. We try to make things as simple as possible. We very frequently have these discussions with customers, and the cost of the extra site and things like that, they decide, well, that was an interesting idea, but we won't be doing it now.
Depends how important that requirement is.
Right, absolutely.
They're willing to pay on it.
Yeah. But we do have a significant number of customers with both of these configurations, and I would say we're seeing an increase in the expectations that customers have for having a system that is completely geo-replicated like this, even if we're talking about a multi-petabyte scale. A couple of other little details. We have a software load balance or virtual IP design that allows you to run the connectors or a process that give you either an SMB or an NFS or an HTTP access to the system. You ask about the questions of performance, so we're limited to the bandwidth of a single connector, obviously, for throughput on a volume, so you can add additional connectors, use virtual IPs to spread the load over a number of connectors, and so that's what we do to provide higher throughput on a single volume, is to add more and more connectors, and you can parallelize the workload through multiple connectors on the system, and then fail over and fail back between connectors on a pool of virtual IPs provided on the system. Another functionality, we made some recent improvements in the file and directory access coordination. There's kind of a conflict between a shared nothing architecture and file and directory access concurrent reads and writes. We've made some significant improvements that allow the system to be just as fast if there's no concurrency on creating new files in a directory, and then obviously the concurrency has an effect on the performance when you have multiple writers to a single subdirectory. And then we've had introduced the functionality that allows us to have multiple readers while writing very large files. This is used quite a bit in the video industry when you're streaming a multi-gigabyte file into the system and you want to start doing editing, coloring, transcoding kinds of works on the file as it's being written. This was the question you asked a little bit ago. We have the HTTP interface to the file system that maintains all the file system tree structure of a POSIX file system. We use our S3 connector that we've talked about before, Zinco, that allows us to have then a full S3 access. This is a simple HTTP access. This is a full S3 access to all of the data in the file system. So basically, you get a presentation in S3 of what you have in the file system.
Okay, and what's the SOFS in this?
The SOFS is what we scale out file system. So this is what we've been talking about.
Okay.
So this is the true POSIX file system, and this is an S3 connector. Instead of going on a simple HTTP REST interface, you're using S3 as a protocol there.
Right.
So the difference is your bucket information, bucket listings and things like that actually come from the directory tree structure on the system. So we're kind of faking the
Yeah,
the names.
it's an object presentation of
Object,
file system,
exactly.
which is what you sometimes need.
Exactly. So-
And from an ACL perspective, basically we just say the S3 sees everything.
So the S3 sees what you configure it to see. That could be a single subdirectory, for instance.
Okay.
And then the rights on the system are a simple list of users that have rights to
But
access the
that's
system.
managed independently from the
Right. That's managed
ACL.
independently from the system's ACLs.
Okay, I was going to say, because trying to figure out a way to map those just sounds
So-
like a nightmare.
Well, it is. We're still thinking about it, but it is definitely quite complex.
Yeah.
Okay.
You also have some control as to what security context the S3 connector itself attaches at.
Yeah,
Right,
exactly.
exactly. Right, absolutely. So here's some example architectures of different systems that we have. We have a system running, a 20 petabyte system. It has a 2-site plus a witness, and so that gives you a total of 54 petabytes of raw data on the system. This is a very interesting one. It's a 17 point. This one has been deployed and isn't completely full. This one is actually pretty much full. 17 petabytes of storage used in the
Time for
automobile.
a follow-up sale.
Used in the automobile industry. There's actually been several follow-up sales that started at about 5 petabytes, and that's grown to almost 20, and we're expecting this one to go 30 or 40 petabytes. So those are some of the larger file systems that we have. A couple of these are interesting because they are the 3-site model, and you can see the 5 to 8.5. You get the less overhead by stretching the system to a 3-site model. If you look at how we play in the industry, I don't want to make a big deal of this, but we would say this is the low latency, the hyperconverged and the all-flash, very low latency, relatively small. Below the axis, the very high bandwidth systems. A lot of systems out here. What we see when you get beyond 4 or 5 petabytes, and you could argue about the numbers, a couple billion files on a single file system, it gets pretty sparse out here. The people that are comfortable doing systems of this size. I think GPFS, possibly Lustre, can be out here in these kinds of volumes, but they're not for general usage. They're usually in the supercomputing space.
And then there's a whole raft of startups.
Yeah, but we're definitely out here in the space. We're pretty comfortable to be in a pretty unique position once you're in the certainly in the double digits, but in the 4 or 5 petabyte range. It's kind of a positioning where it's very, very interesting to use this technology. Few examples from the media and entertainment space. This technology has become quite popular in the media space. A number of different companies. Molotov is a very interesting new startup that basically takes all of the TV feeds and users can decide that they want to program a number of recordings and then use it as a on-demand video recorder in the cloud. And so that it's expected to grow and grow and grow as the collection of things that have been recorded grows over time. I'd like to talk a little bit about some research projects we're doing. One of them will tie back to Zinco, but we'd applied for a number of research projects, and we ended up winning 2 of 3. I'm glad we didn't win the 3rd because it's been quite a bit of work to work on these. One of them is called Rainbow FS, just right consistency for scalable file systems. It's working with a number of different universities. This project was initiated a couple years. The concept of this Rainbow FS is you have red consistency, which is full consistency, blue consistency, which is eventual consistency, and being able to have a system that's somewhere in the right place in the middle for a distributed system. One of the things that we're investigating with this is the possibility of having a file system that's worldwide geo-distributed, and you can have active use, and then using rules-based system to merge the file trees together and create a consistent image over time of the system. So basically being able to work on a file
Multi-master
system.
replication file system.
Exactly.
That's scary.
So this is a research project that we'll see where it ends up, but it's been very helpful to work with university researchers in understanding better the constraints of having these just geo-distributed systems and making sure that we follow the rules and be able to tell our customers clearly what are the guarantees that we're providing them from a consistency perspective. Second project is called LightKone. It's a edge computing. You can think about this as edge computing, fog computing. This is working together with 4 different research institutions, 4 different industry partners. We're the only storage company involved in this project, and lots of different things we're thinking about doing. One of them is adding a distributed indexing. We talked about the Zinco model, being able to introduce a partial indexing at the edge. I think it was brought up a little bit earlier. Could you use some additional compute resources to add metadata to the system? One of the things we're investigating here, for instance, if you're storing images, being able to use AI and tag in anything that you're able to determine about an image that you're storing into the data as it's going into the system.
So we're going to have not hot dog in the extended S3 metadata?
Get Enrico on that one. Yeah? So that's his thing.
Or man, it might be the possibility of doing things like adding full text search or other things on the edge of this whole notion of fog computing, partial indexing. So what we'll get out of this, we're not completely certain. It's very interesting to investigate and think about the possibilities of adding edge computing into the approach. That together with this notion of the cloud's Lambda functions, where you can provide actions that are performed on objects as they're stored. Cisco has a very strong team of people working on this fog computing notion, where the network is the computer, is kind of their.
Don't use that one. That's how we ended up with a Java station.
But anyway, so it's a very interesting thing to think about, and this is also involved in the whole. The LightKone is a little bit of a geek thing about the providing consistency models that can support very high latencies on your system. So that's what I had to say about the file system.
Brad, why the move away from just object? Was that always part of the company's DNA to sort of try and become more of a data company than just an object storage company? Was that an opportunity in the market? Was it, because obviously it's quite a direction to go off and grab 2 different things.
Are you referring to object to file system or?
Well, the company was originally an object storage company,
right.
but you're focusing on file system, and that could be quite happily sold to companies who have no interest in the fact that there's an object store underneath that.
Right.
So it's like another segment of the market.
Or just go partner with SoftNAS or something.
Yeah.
Yeah. So I think it's a very interesting question, and we started with a pure object model. We wanted to provide an object system that was quote unquote infinitely scalable, that was very highly available. We found out that the industry has file system interfaces, and file systems are disappearing like tape is.
But they're still there.
Like tape is.
Exactly.
After the nuclear apocalypse, we will have tape and cockroaches.
So that pushed it to do file system interfaces, and we actually the S3 we weren't sure about. Then S3 became much more obvious as a protocol, so we reinvested in S3. And I think reinvesting in an S3, we really started noticing that our customers were talking a lot more about cloud. Now they're talking about file system in cloud. They're talking about everything in cloud, and so that pushed us back into the cloud space. And so it's in a lot of ways we're following our customers' lead into what they're asking us for.
And I just add a little bit actually on the file system side. So following where the customers want to go in adding the file system, but we could have got there, with an OEM.
Yeah.
We didn't, because that would have added another layer of availability challenges, right? It's a different application, different platform. This instead, it's built into the platform itself, right? That's why we actually went and built our own index
On
tree.
that question, so from a metadata perspective, right, you got your object storage and you're storing that, I get that. It sounds to me that when you layer the file system stuff on it, that the amount of metadata, the size of the metadata database that you now have grows much bigger. Is that a correct statement?
Actually, no. The one really interesting thing, we're kind of anti-gateway people, I would say, because the problem that we always saw with the gateways is you get this file system gateway that's got this single point of failure, and it's got this growing pool of metadata. And it's one thing when it's a 500 terabyte file system. We do have file systems with several billion files in them, and so that becomes a very complex problem. But because the metadata is completely distributed, it grows in proportion to the number of the servers. And actually the quantity of metadata on the SSDs to do a giant file system like that is really pretty modest.
I mean, just over a pure object is just a modest increase?
Right, so we're looking at, give you a number, a typical server, 10 terabyte hard drives will have 4 terabytes of SSD associated with it, something like that. And that's enough for a file system. The only time we would get into trouble with if the files are all extremely small or something like that. But otherwise, the size of the metadata that's required to do all the directory structures, it's really.
You just add nodes and spread it out.
Right, and it grows naturally with the system, but the ratio of data to metadata is very, very high.
All right, cool.
So on the file system, I saw it was SMB2. When does SMB3
So
support?
we support all of SMB3 except the
Failover mechanism?
transparent failover.
Okay. You support the RDMA?
No.
You don't do no ODS, right?
Yeah, I wouldn't expect.
But that's the most esoteric one. But the transparent failover is something that we don't support today. But otherwise we support. And we're the numbers where we get about a gigabyte of throughput on a single SMB connector, that's SMB3. SMB2 doesn't come close on that one. But I think we're just about as good as anybody in the industry on SMB3. We have a number of platforms that are running at a gigabyte per second throughput on connectors and on the system.
Okay.
And again, the namespace between SMB, NFS, and HTTP is identical. It's the same inodes, the same everything. And Fuse as well, except we don't publish, we don't sell anything, do anything special with the Fuse connector.
Okay.